Earthquakes are the largest potential sources of casualties for inhabited areas, leaving cities in disaster and killing tens to hundreds of thousands of people. Damage to structures not only causes loss of human lives and disruption of lifelines, but also long-term impact on the local, regional, and sometimes national and international economies. The reliable prediction of nonlinear structural behaviour and the failure mechanism during severe seismic events has proven to be an extremely difficult task. Experimental research is therefore critical towards better understanding and predicting the seismic response of structural components. There are several different experimental techniques that can be used to test the response of structures to verify their seismic performance. One of these is the use of an earthquake shake table, where structures are excited in such a way that they are subjected to conditions representative of true earthquake ground motions. However, due to the expensive costs, complexity, damage to the equipment, and the limitations on the size and capacity of these earthquake simulators, structures are typically tested on a reduced scale or a highly simplified model is used. The scaled and simplified model does not necessarily represent the response of the full-scale structure, which questions the validity of the shake table tests. Hybrid simulation, which is also called the pseudodynamic test method, is an attractive alternative for shake table tests. Hybrid simulation is a hybrid procedure that combines classical experimental techniques with online computer simulation for cost-effective large-scale testing of structures under simulated dynamic earthquake loads. Hybrid simulation facilitates the study of structural response by experimentally testing only the critical portion of the structure, while the rest of the structure is modelled numerically in the computer. At each step of the analysis, the governing equation of motion is solved, similar to pure numerical simulations using a time-stepping integration. The calculated displacement demands are then sent to the lab and applied to the physical specimen using computer-controlled actuators, while the numerical portion is analysed on the computer. The resisting forces, including shear, axial and moment reactions, are measured and fed back to the computation solver to calculate the displacements corresponding to the next time step. This process is repeated until the ground motion is concluded. Multi-axis substructure testing in the Smart Structures Laboratory at Swinburne provides a powerful tool for investigating the effects of earthquakes, hurricanes and other extreme events on large structural components using hybrid simulation testing. A sophisticated 6 degrees of freedom control system is used, utilising 8 high-capacity hydraulic actuators that enables application of complex multi-directional deformation or loading schemes to structural components. In addition, a rigid steel crosshead is used to apply triaxial control, yaw, pitch and roll, to the test structures and also to apply planar translations to planar substructures. The system features mixed mode control, allowing users to specify the position or force required for the desired direction of loading to test large-scale structural components, including portions of beam column frame systems, walls, tanks and bridge piers. The popularity of hybrid simulation amongst structural engineering researchers has grown to a great extent. Geographically distributed testing is one recent concept that has been developed from the use of substructuring techniques and benefited from technological advances in data transfer and computing. The concept of geographically distributed testing is that individual substructures do not need to be within the same facility, but can be linked by either the internet or other methods of data transfer. Therefore, laboratories with much larger capacities can be used for experimental subassemblies. In terms of the numerical portion of the hybrid simulation, there are also benefits in allowing for the use of more powerful computers or even supercomputing facilities to run the hybrid simulation test, since the computers running the analysis do not need to be in the same laboratory. For example, to evaluate the seismic response of a bridge, a multi-site hybrid simulation can be carried out. The column of the bridge can be tested in the Smart Structures Laboratory at Swinburne that is able to perform multi-axis substructure testing, while the pavement of the column can be tested in another facility across the country, and the rest of the structure can be modelled numerically in a facility with supercomputers, for example, the University of California at Berkeley. The multi-axis substructure testing system in the Smart Structures Laboratory provides a powerful and cost-effective tool to investigate the dynamic effects of extreme loading events on large-scale structural systems through local or distributed hybrid simulation testing.